Simplifying rational expressions. A rational expression is a ratio of two functions, say f of x and g of x. F of x and g of x are polynomials. And because of the structure of the expression, where it's a ratio of two terms, we cannot have the denominator equal to 0. So we are unable to have g of x equal to 0 in order to have a defined expression. So this is an example of an expression, but I could make this a function. We could call this h of x, in which case this would be a rational function. But we're just going to focus on expressions in this video and how to simplify them. So when it comes to simplification, we'll jump over to an example. This is a rational expression. In the numerator, we have a monomial term, and in the denominator, we have a monomial term. And to simplify this, what we're going to look at is what can we cancel out that exists in the numerator and the denominator. And then we'll break down why the cancellation works. What we might say first is let's focus in on the numbers. 15 is not evenly divisible by 9. But if we imagine that that was a standalone fraction, which these are with just a few more terms, we would simplify that by dividing both of those by 3 because they share that common factor. So I could reduce this down into 5/3 when I'm just looking at the number. Then when I move over to the x variable, x squared means there's 2 x's up top. X to the 4th means there's 4 x's on the bottom. So I can cancel out something that's on the top that exists also on the bottom, but I can't cancel out more than what is present. So at most, I can take away 2 from the top and the bottom, which would leave no x's left on the top, but 2 left over on the bottom. And then if we look at the y's, we have 1 on the bottom and 5 up top. So if I remove 1 from the bottom and the top, that leaves none left over on the bottom, but 4 left over on top. And here is a simplified version of that rational expression. Now, why does that work? Well, let's expand out what is happening here. We could say 15 is equivalent to 5 times 3, and 9 is equivalent to 3 times 3. And I'm going to make sure things line up so we can see exactly what happens. So we have x times x, x times x times x times x, and then we have the y's. So we have times y times y times y times y times y, and then times y. When we cross something out from the top and the bottom, here, 3 divided by 3, this is equal to 1. And we know that multiplying by 1 does not change the value of an expression, or even dividing by 1 doesn't either. So we are allowed to remove things that are equivalent to a value of 1 because we know that we won't change the value of the expression. So the cancellation must be something that when we divide them, we get 1. So now we can make that cancellation. We see x over x, this is also equal to 1. Equal to 1. Now there's no other x's to form a ratio that is equivalent to 1. So I'm done. There's 2 left over on the bottom, which we can condense back to x squared. When I take care of the y's, y divided by y is equal to 1. There's nothing left over to format a ratio equivalent to 1 with the y's, with what I have up top and what exists on the bottom. So I recondense back down. Then we'll see that in total we have what we originally found. But the cancellation works because canceling something from the top and the bottom is equivalent to a value of 1. And I know when I make that cancellation, I am not changing the value of the expression, and that's important. We can't change the expression's value through a simplification. We're just changing the way it looks. And we'll see why that's important in another example when we deal with polynomials. But before we move on, we want to be able to identify where expressions are undefined as well. And when we do that, we have to consider the original denominator. Because when I look at the finalized simplified version, you're going to notice that the y isn't present in the denominator of the simplified version, but it must be considered in the original to make sure we know what values of y cannot be taken for this thing to be defined. So, cannot equal 0. We have a product of three things equaling 0, so 0 product property. We could split this. 9 does not equal 0, obviously, so we can ignore that. Solving x to the fourth equals 0, we get x cannot equal 0. This is already solved. So these are the two values which x and y cannot equal if we want our expression to be defined. So make sure you consider the original denominator when identifying values for which the expression is undefined. Now let's move over to an example that has polynomial terms. One of the most common mistakes when simplifying a rational expression is by identifying a piece of the polynomial and canceling it with a piece of the polynomial in the denominator. So for instance, many people will cancel this and this. That is not allowed. Remember, even though that ratio equals 1, we want to make sure when we make a cancellation, we do not change the value of the expression. So to simplify what I mean by that, let's say we take x plus 1 over x plus 4. If you think you are allowed to cancel the x's, just remember that x represents the value of some number that we choose. So let's say say x takes on the value of 1. If x were to take on the value of 1, the value of this expression would become 2/5. And if we think we can make that cancellation, then the value of the expression would be 1/4. But we said with a cancellation, the value of the expression should remain the same. And because of the fact that it doesn't, we can learn from this example that we are not allowed to split pieces of a term. We can only cancel out entire terms together. So an entire binomial with an entire binomial. We cannot split a binomial by crossing out a piece. So when I look at the trinomial in the top and the trinomial in the bottom, I am not allowed to break up or cancel out pieces of those trinomial expressions. So what we want to do when we have polynomials is to identify pieces that can be canceled, is to factor each expression. So through factorization, in this example, we have a values greater than 1, so we're going to have to use that split the middle. So we'll do the numerator first. Splitting the middle, we're going to do a times c, which gets us 12. What multiplies to 12 adds to 7. We're going to get 3 and 4. So we're going to split the middle. Then we have a grouping problem. We'll take out a 3x. We're left with 2x plus 1. What do I have to remove from the second group so that I'm left with 2x plus 1? We'll see we have to remove a 2. Both of these expressions have 2x plus 1, so we'll factor that to the front, and what's left over is what was in front of each parenthesis. So there's our factorization of the numerator. Now let's do the denominator. A times c is negative 36. What multiplies to negative 36 adds to negative 5. Negative 9 and 4. We're going to split the middle, or the linear term, into two pieces so that we have a grouping problem. We remove a GCF from the first group. We're left with 2x minus 3. We can see if we remove a 2, we're left with 2x minus 3, which is what we want. 2x minus 3 gets factored out of the two terms. What's left over is 3x plus 2. There's your factorization. So let's put that up here. Now, when we restructured these trinomials into a product of two binomials, we can see now that we can cancel out the 3x plus 2 from the top and the bottom, because when I box this off, that ratio is equivalent to 1, and it is multiplying by 1. Multiplying by 1 is the key. So it's not just the fact that the ratio is 1, but when we identify the ratio, we want to make sure it's the multiplying by 1. So this is equal multiplying by 1. And we know multiplying by 1 does not change the value of the expression. Here, if we were to box this off, yes, that equals 1, but we're not multiplying by 1 in that scenario. We would be, I don't even know what's going on. We have a plus and a minus here. So adding 1 or subtracting 1 definitely changes the value of something, right? If we take 2 and subtract 1, it becomes 1. But if we take 2 and multiply by 1, it still remains at 2. So we want to recognize with cancellations, the equivalent ratio must be multiplication by 1, okay, not addition or subtraction. So that's a big, big concept that we need to understand in this unit. And now that we've identified that we're just multiplying by 1, we can make that cancellation from the top and the bottom. And now, as a final result, we have 2x plus 1 over 2x minus 3. Again, you may be tempted to cross out the 2x's. And yes, you are right that 2x over 2x is equal to 1, but we're not multiplying by 1 in that scenario. And we need to multiply by 1 in order to make the cancellation. So that is not a valid cancellation, and therefore what I have here in green is the final answer. This is a fully simplified version of the original rational expression, and let's identify the values for which the expression is undefined. To do that, we must solve the original denominator. The original denominator, solving a quadratic, so we would set it equal to 0 and solve. Factoring would be a way to solve it, and lucky for us, we've already factored it. So if we want to know when this equals 0, we just set each piece equal to 0, and we solve. And we're going to get x cannot equal 3/2 from the first one, and x cannot equal negative 2/3 from the second one. So again, if you didn't consider the original denominator, but only the final denominator, you would have gotten this one right, but you would have missed that second undefined value. And to conclude with the last example, we'll go a little quicker now that we kind of understand what's going on. Look to factor when you have polynomial expressions. So if we have monomial expressions in the numerator and denominator, we don't have to factor because we can't. So up top, what might I do? There's no c term in that quadratic, so I'm not going to split it into the product of two binomials, but we can look to take out a GCF. Let's take out an x, negative x plus 3. And on the bottom, we'll have to do the split the middle because we have an a value greater than 1, so there's no shortcut there. So 2 times 3 is 6. What multiplies to 6 adds to negative 7, negative 6 and 1. So we're going to split negative 6x minus x plus 3. Grouping. Take out a negative 1 so that the parentheses match. Factor out the parenthesis value. What's left over is what was in front. There's the factorization. And I'm actually going to reorder it so we can notice something here, which is why this example is brought up. What we have up top, negative x plus 3, and then on the bottom, x minus 3. Pretty close, but not exactly the same. The only difference is the signs are switched. So if you notice that, to get the signs to switch, you can just factor out a negative 1 from either the parentheses, because that changes the signs of the expression, and then we can make a cancellation. So if I factor out a negative from the top, we'll be left with the x minus 3. Now we can see that we have a ratio that's present. This divided by that equals 1. And by sectioning that off, that is multiplying by 1. So that is a valid cancellation. We can cross out this from the top and the bottom. We have negative x over 2x minus 1, and that is the best we can do. We can't cross out those x's, right? Because yes, dividing them equals 1, but we're not multiplying by 1 when I identify that ratio. So to beat a dead horse here, the ratio you identify that equals 1, the cancellation you think you can make, should be showing that you're multiplying by 1, not adding or subtracting. So this is our final answer. To identify where the function is undefined, we look at the original to solve the original quadratic. Factoring is a valid solution in this case. We've already factored it. So set each piece equal to 0. From the 0 product property, we'll get x equals 1/2, x equals 3. And remember, that's not what they actually equal, but what they cannot equal. So there are the two values for which the expression is undefined, along with a simplified version of the original rational expression. So there's a video on how to simplify rational expressions.